Okay, let's initiate the simulation. The target for today's deep dive is a big one, the human protocol known as altruism. Time to deconstruct the code.
Here's our diagnostic roadmap for today. We're going to define the core protocol, pinpoint a critical system failure, run a simulation of that exploit, and then analyze a couple of proposed patches. After all that, we'll run our final analysis on the integrity of the whole network. All right, let's get into it.
All right, first things first, we have to define the protocol itself. Before we can even think about finding bugs, we really need to understand the fundamental parameters of this core operating system. So what are we really looking at here? Well, the baseline definition is pretty clear. The altruism protocol basically triggers an action that helps out another node in the network, and here's the kicker. It's often at a direct cost to the user. This cost-benefit function is absolutely central to how the whole thing operates.
And this is where it gets really interesting. The protocol isn't simple. It's more like it's running on a dual-core system. On one side, you have the psychological processor. It's all about intent, running subroutines like pure empathy. But running in parallel, you've got the biological processor. And that one? It's completely outcome-based. It's laser-focused on the reproductive consequences, making sure shared code survives. So you've got two very different pathways that, surprisingly, often lead to the exact same result.
Now we get to the real meat of the problem, the core conflict of our entire analysis. We found a critical vulnerability, a major clash right inside the human reward system, which is what the whole altruism protocol depends on. And our source material, from Dr. Anna Lemke, really nails the primary attack vector here. The modern world is just saturated with these high-reward, low-effort stimuli. It creates this constant, high-bandwidth stream of dopamine that can just completely overwhelm the system's intended functions. It's wild.
And this brings us to what we're calling the dopamine clash. You've got two competing pathways. On one side, there's cheap dopamine from consumption. Think of it like a system exploit. It's easy, it's potent, and it leads to tolerance and isolation. But on the other side, you have adaptive dopamine, which comes from real connection. It's an internal release that actually reinforces the social network. The problem is, the system just wasn't built to handle the sheer volume of that cheap stuff.
So, to really see this vulnerability in action, we're going to run a simulation. It's based on some pretty fascinating and, frankly, disturbing experimental data. Let's execute the exploit and watch what happens.
The data from this experiment is sequential and just incredibly stark. Step 1, the baseline. The pro-social protocol works perfectly. A free rat sees its peer trapped and instinctively helps it out. But then comes step 2, system intervention. We introduce a high dopamine exploit. And the result? Well, it's a catastrophic failure. The drive to be social is completely suppressed. We're talking a total resource allocation error, where the system prioritizes the drug over its own network peer.
And there you have it. The simulation result is conclusive. This high-potency dopamine input triggers what's basically a denial-of-service attack on the empathy module. The altruism protocol is, for all intents and purposes, taken completely offline.
So if the system's broken, how do we fix it? That brings us to the debugging phase. And the first proposed patch isn't a new piece of hardware or a drug, it's a social algorithm, radical honesty. Let's take a look at how this actually works as a debugging tool.
The mechanics of this are actually pretty elegant. By forcing a user to tell the truth, which, can be painful in the short term, it creates the conditions for real long-term intimacy. And that intimacy triggers the release of that adaptive dopamine, the good stuff, which restores the healthier system-reinforcing reward loop. Plus, as a side benefit, it seriously reduces the cognitive load of having to maintain a bunch of lies. It just frees up processing power.
Okay, but debugging one user isn't enough, right? How do you scale this fix across the entire network? Well, that brings us to the next phase. We have to recompile the social fabric. And the key to doing that is this concept called club goods.
So what exactly is a club good? You can think of it as a piece of social technology. It's basically a shared resource, like group stability, that actually becomes more valuable the more that members contribute honestly and play by the rules. It's a cooperative system that strengthens itself.
And recovery groups are a perfect real-world example of this. They function just like a social operating system. When one user inputs radical honesty, say admitting a failure, the system doesn't crash. No, instead it triggers a process call for all the other users to run their own empathy and altruism protocols. The output actually reinforces the entire network and strengthens that social glue.
It's brilliant, really.
All right, let's pull all the way back now for our final analysis. We're zooming out to the macro level to figure out the ultimate purpose of this altruism protocol. What is its evolutionary imperative? I mean, why does this code even exist in the first place? And here it is, the key takeaway. Altruism isn't just some nice-to-have kindness feature. It functions more like a vital, open-source contribution to the stability and functionality of the entire human operating system. Let's just quickly break down how this all contributes to network stability. Every one of these subroutines offers a clear benefit. Kin selection is about making sure shared genetic code survives. Reciprocal altruism builds the P2P trust you need for sharing resources. And group-based altruism just gives the whole local network a competitive edge. The point is, a robust altruism protocol isn't optional. It is a core feature, absolutely essential for long-term network survival. It's not a bug, it's the whole point.
So, our analysis leaves us with one critical and honestly pretty unsettling query. In an environment that is saturated with infinite cheap dopamine, an environment this protocol was never designed for, is this core component of the human OS facing planned obsolescence? The integrity of the entire network may very well depend on the answer. Simulation complete.